For the next topic, we'll consider one-sided limits, so they're slightly more general concept, and let's see a little bit where that comes from. So up until this point, the limits that we've computed, if we took, for instance, the function that had a jump, we always were able to say, well, if I approach the value from the left, I get a special value for my limit, and if I approach my value from the right, I get that same value for the limit. So it didn't matter whether you approached the limit point from the left or from the right, you always got the same answer. But that is not always the case, and for instance, to see what happens, let's try to compute the limit as x goes to pi over 2 of the function tan of x. So if we look at the graph of tan of x, we know that special things happen. For pi over 2 and for negative pi over 2, we have these vertical asymptotes. What that means is that the graph of the function comes in from negative infinity, goes through 0 like this, and then climbs to plus infinity as x gets closer and closer to pi over 2. And then it does the same thing when you go beyond pi over 2, so it comes in from minus infinity, goes through 0, and then climbs back to infinity for x here equal to 3 pi over 2. So this puts us a little bit in a strange position. So if we approach pi over 2 from the left, so if we put ourselves slightly below pi over 2 and we walk towards pi over 2, we see that the function values get bigger and bigger. So the function escapes to plus infinity. And so here this going to pi over 2 from the left will denote this as x goes to pi over 2 minus, and we get that the limit here is plus infinity. So it becomes positive and bigger and bigger. On the other hand, if we put ourselves slightly above pi over 2 and we walk back towards pi over 2, then what we see is that the function goes to minus infinity, becomes smaller and smaller, less and more negative, and the values go to negative in infinity. So here from the right, and this is denoted by x goes to pi over 2 plus, we have that the limit is equal to minus infinity. And so we have a situation in which the limit itself does not exist, but one-sided limits so the limit of x going to pi over 2 minus, so from the left-hand side, and from the right-hand side, x going to pi over 2 plus tan over x. These two exist. And so one-sided limits are you walk towards a point but just from one side, from either from the left or from the right. So let's turn that into a more formal definition. It's going to be very similar to the definition of a limit. So if a function f is defined on some interval b a, and that's an interval that's left from axis a. So by the way, here we will just define the left-sided limit. And so let's make a small drawing as well. So we have our function, which is, and we want to compute the limit for a given value a. And we know that the function is defined on an interval ba, which doesn't have to include a itself. So it's defined on some interval ab left of a, and f of x approaches a value L as x approaches a from the left, then we say that f has a left limit L at x equal to a. And the notation here is lim x going to a plus f of x equals L. So now for right-sided limits, you just have to switch left and right everywhere. So let's do that in blue. So here the function also needs to be defined on some interval that's to the right of a. And here x has to approach a from the right. And then we say f has a right limit, and we denote lim x going to a minus f of x is L. And so we had the picture here for the left limit. We can also make a picture for the right limit. So here we take our point and we approach from the left, and for the right limit it's from the right. So we have a function that's defined on some interval a c to the right of a, and maybe the function is defined somewhere else as well, but don't really care about that. And what I do is I approach a from the right. So that's the definition, and then a theorem. So the limit exists, the two-sided limit. For x going to a is equal to a value L if and only if both one-sided limits exist and are equal to the same value. So if you walk to x from the left, you get L, and if you walk to x is a from the right, you also get L. So that's enough theory. Let's do a couple of examples. So for the first example, we'll compute the limit of the square root of x for x going to 0 from the positive side. So if you draw the square root function, it looks a bit like this. And in particular, it's not even defined for negative values. So we can't talk about the limit. We can only talk about the right-sided limit. And you know what happens if x becomes smaller and smaller but stays positive. Square root of x also becomes smaller and smaller. So the limit here is equal to 0. The second problem, we're going to look at a slightly different function. So we'll look at the limit of x going to 0 of the function absolute value of x divided by x. So this is again a function that we have to maybe unpack a little bit, make a drawing. So the function absolute value of x, you can also write it as it's just x if x is bigger than or equal to 0, and it's minus x if x is negative. And so that means that we can also write absolute value of x divided by x as a piecewise defined function. So it's x divided by x, or plus 1 if x is positive. It's minus x divided by x, which is minus 1 if x is negative, and it's undefined if x is equal to 0. So that function looks like this. It's constant minus 1 up until where you hit the y-axis, and then it's not defined for x is equal to 0, and for positive x it's the constant plus 1. So now from the graph you can see that the left limit x going to 0 minus of the function, that's the limit of x going to 0 minus of minus 1, and that's just minus 1. But on the other hand, limit x going to 0 plus absolute value over x is limit of plus 1. So that is plus 1. And in particular, we see these two values are different. So the limit for x going to 0, the two-sided limit, does not exist. And that's because these two values are different. For the next example, we'll do something a bit more involved. Here we take the limit for x going to the value 2 of x minus 2 absolute value again, divided by x squared plus x minus 6. So let's do two separate cases because we know we're dealing with an absolute value. And actually, before we do that, let's write this as x going to 2 and factor out or factor the denominator. So you can write the denominator as x minus 2 times x minus 3. Sorry, x plus 3. And let's start with the case of x going to 2 from the left side. So in particular, we know here that x is going to be less than 2. So then our limit becomes x minus 2, x plus 3 is the limit of minus x minus 2 divided by x minus 1, x plus 3. And we see here that we get a nice cancellation of the factor x minus 2. And we can write this as limit x going to minus of minus 1 divided by x plus 3. That is a continuous function. You can substitute the 2 in there and you get minus 1 over 5. And now for the other case, we do x going to 2 plus. So in particular here we know x is going to be positive, and that's important to figure out the absolute value. So x2 plus x minus 2 absolute value over the denominator is limit of x going to 2 plus x minus 2, x minus 2, x plus 3. Again, the x minus 2 cancels. We're left with x going to 2 plus 1 over x plus 3, and that is plus 1 over 5. So again, the one-sided limits here exist, but these two values are not equal. So the overall limit of the function does not exist. And for the last example, let's pull together a couple of different functions. So here we want to compute the limit of x going to pi of f of x with f of x equal to sine of x when x is less than pi, and square root of x minus pi for x bigger than or equal to pi. It's an odd looking function, but we can try to graph it. The value pi is here, and for x less than pi we have a nice sine curve. In particular, it looks a bit like this, and then so on. And then for x bigger than pi, we have square root of x minus pi, and that looks a bit like this. In particular, what you see here is that the function is continuous. So you can trace through this without lifting your pen, but it's not smooth in the sense that there's a little bit of a corner here. So all of a sudden you go from smoothly like this to changing when you go into that other branch. That doesn't matter for the limits. All that matters is that you don't have to lift your pencil, the continuity. So the limit x going to pi minus of f of x is the limit x going to pi minus of sine over x. So here again we're to the left of pi and we're approaching pi, so we get that our values also approach sine of pi, which is 0. And on the other hand, limit x going to pi plus is the limit of square root of x minus pi. So that gives us square root of pi minus pi. It's similar to the first exercise that we did, and this is 0. These two values are the same, obviously, so here we conclude that the limit for x going to pi of f of x, it exists, and it is equal to 0.